Hi guys, today we're going to go through displacement reactions. Before we do that, I'm hoping you've all seen part 1 and I'd like you to pause the video and have a go at completing the following reactions using the rules that we looked at last lesson. Once you've done that, I want you to have a go at writing the balance symbol equations using the rules for formula ions and making sure that the charges add up to 0. So if you could pause that now and then we'll go through them. Okay, let's go through the first one. So we've got copper plus bromine. Remember, the number in brackets represents the charge of the metal ion. So we know that the copper will have a positive 2 charge and bromine has a negative 1 charge, so that's going to be really helpful when we write our formula. But this bit's quite easy. We've got copper plus bromine, that's going to form copper bromide. Right, next, zinc plus sulfuric acid. Remember, metals plus acid form a metal salt and hydrogen gas, so we're going to form zinc sulfate plus hydrogen. We've got sodium carbonate plus sulfuric acid. Remember, because this is a carbonate, we're going to make carbon dioxide gas. We're also going to make water, but we're still going to also make a metal salt. So the metal will be sodium, the salt is sulfate, so sodium sulfate plus carbon dioxide plus water. And the last one, potassium bromide plus silver nitrate. This is actually a really good example of what we call a displacement reaction. We've got potassium here, which is more reactive than silver nitrate. So what's going to happen is the potassium is going to displace the silver and going to form potassium nitrate and silver bromide. Right, okay, so that's the first bit done. Now we want to write out the balance symbol equation. So for the first one, copper, simply Cu. Remember, group 7 elements like bromine are diatomic molecules, so we Br2. Now if we remember, the charge of copper is Cu2 plus. The charge of each bromine is a negative. So in order to make these charges add up to 0, our ratio of ions needs to be, for every one of these, I need 2 of these, and therefore my formula will be CuBr2. And we're going to follow that same principle for the others. If you're still struggling with this, go back to the previous video. Zinc plus sulfuric acid, zinc plus, remember, you need to know the formula of sulfuric acid, H2SO4. You need to know the charge of each sulfate is SO42 minus. Each zinc has a charge of +2, so our ratio would be 1 to 1. And hydrogen is a diatomic molecule. We'll just quickly check that it's balanced. Yep, 1 zinc, 2 hydrogens, 1 sulfur, 4 oxygens, 4 oxygens. Right, the third one, we've got sodium carbonate plus sulfuric acid. So sodium carbonate has a formula of that. So remember, the charge of a carbonate and the charge of our Sodium needs to add up to 0. Sulfuric acid, is it sulfuric acid again? Number 3, yep, H2SO4. And we're going to form sodium sulfate, Na2SO4. Remember, each sodium ion has a charge of +1, so we need 2 of these for every one of these, plus carbon dioxide plus water. Again, you're expected to know the charges of those compounds, carbon dioxide and water. And the last one, number 4, we've got potassium bromide plus silver nitrate. Remember, our nitrate has a -1 charge, and we can see that the silver has a +1 charge, so our ratio will be 1 to 1. We form silver bromide, AgBr plus KNO3. And well done if you've got all of those correct. Okay, let's move on to displacement reactions. So I've got a bit of an animation here, so I'm sure you'll be very impressed with my drawing skills. We've got here an illustration to really help us understand what displacement reactions are. So we've got sulfate, and let's say that sulfate is a female, okay? And sulfate, if we remember from part 1, has a -2 charge. Now, when sulfate bonds with another metal, in this case, we can see that magnesium is wanting to bond with sulfate, you would form what we call magnesium sulfate. Now, let's say that these 2 ions have formed a bond, they've formed a connection, they've made this compound magnesium sulfate. Now, let's look at what happens when this cheeky chappy, calcium, with his tongue pointed out, quite confidently says to sulfate, hey, sulfate, I can give you electrons quicker than magnesium. Now, what we need to do at this stage is reference the reactivity series. And last lesson we said that metals that are more reactive have a greater tendency to lose electrons and form positive ions. So the quicker a metal can form a positive ion, the more reactive it is. Now, if we remember from the reactivity series, calcium is more reactive than magnesium. So let's look at what's happened now. It looks like calcium has bonded to sulfate, and we can see here what's happened to magnesium is magnesium's been left all alone. Okay, now actually I've just realised I've made a mistake here. Because he's been left all alone, what actually happens is magnesium gives magnesium its 2 electrons back. Okay, let's put an electron in each hand. And magnesium actually loses its charge as a result. Now, next lesson we'll look at what actually happens in terms of electron transfer in these kind of reactions. But it's really important just for now for us to realise that a more reactive metal can take the place of a less reactive metal, even if it's bonded to another compound. Right, now what I'd like you to do first is, I'll just cover this up, let's look at exactly what's happened here. So, what has just happened? Magnesium sulfate bonded, magnesium was bonded to sulfate. When calcium came along, calcium displaced magnesium from the compound and bonded with the sulfate. And as a result, magnesium was left alone. Okay, Now, if I was to write this as a balanced symbol equation, okay, I can recognise quite easily here that I've got magnesium, calcium, calcium and magnesium. You can see here that sulfate remains unchanged. It's always SO4 and it always has the same charge. But what did change was the metals it was bonded to. Now we call these kind of reactions displacement reactions. So this is a really important definition for us to know. It's when a more reactive metal displaces a less reactive metal from an aqueous solution of its salt. Now, if you look closely, you can see I've put some state symbols here. We've got an aqueous solution of magnesium sulfate. So pure calcium would be in the solid form, okay? Now, when it reacts with this solution, it displaces the magnesium and bonds to the sulfate, and as a result, we formed a new aqueous solution and essentially solid particles of magnesium. Now, what I'd like you to do is I'd like you to use this example to have a go at completing the following reactions and also writing out the balanced symbol equation in the same way that we did earlier on. So firstly, use your reactivity series. Which metal's more reactive? Will it displace the metal in the compound? What will the products be? And then write the balanced symbol equation, please, with the state symbols as well. Okay, so just pause the video now and have a go. Right, let's have a go at these. Okay, so what we've got here is copper sulfate plus magnesium. Okay, now we can see from our reactivity series from earlier on that magnesium is more reactive than copper, so the magnesium will displace the copper and instead we will form magnesium sulfate and copper, right? So magnesium sulfate plus copper, okay? And we know that this has happened because magnesium is more reactive than copper. Let's do the word equations first and then we'll get on to the symbol equations. Right, same thing here. So looking at my reactivity series, sodium is above magnesium, so sodium will displace magnesium and instead we will form sodium iodide and magnesium. And aluminium is more reactive than iron, so it will displace iron out of this compound and will form aluminium chloride plus iron. Okay, let's get on to writing out the balanced symbol equations. So copper sulfate, if I just write above the charges and make it a bit easier for us. So copper, we can see, has a 2+ charge, Cu2+. Sulfate, SO4, 2-. Magnesium, a pure magnesium, has no charge, and so the magnesium sulfate, Mg2+, sulfate is still SO4, 2-, and again we've got pure copper. So let's write this out as an equation. So what we will have is, because our charges add up to 0, our ratio of ions will be 1:1. So we'll have Cu SO4, remember it's an aqueous solution, plus magnesium, pure magnesium will be solid, and will form these charges add up to 0. So we'll have MgSO4 plus Cu. Oh, I forgot the state symbols. That will be aqueous. This will be solid. And well done if you got that correct. Okay, right. The next one, magnesium iodide. So magnesium iodide, remember, magnesium is Mg2 plus ion, and iodine has a single minus charge. So for every one magnesium ion, I'm going to need 2 iodines to make these charges add up to 0. So it will be Mgi2, remember, aqueous, plus sodium, simply Na, and that makes sodium iodide plus magnesium. So remember, sodium has a charge Na plus, this has a -1 charge. Our ratio of ions would be 1 to 1, so it would be NaI, aqueous solution, plus magnesium solid. Let's just quickly check if this is balanced. I've got 2 iodines here and only 1 on this side, so I'm going to put big 2 in front here, and that then makes me have 2 iodines but also 2 sodiums. So if I put a 2 here, then I've now got a balanced equation. Once again, well done if you got that correct. Let's do the last one. We've got iron 3 chloride. So my iron has a charge of 3 plus. My chlorine has a charge always, it's a -1 charge. So for every 1 molecule of iron, I need 3. For every 1 iron ion, I need 3 chlorine ions. That's quite a mouthful. So FeCl3 plus aluminium. I'm sure you can see the trend here now. And I've got aluminium chloride. Aluminium has a charge of 3 plus, and therefore I'll need 3 chlorine ions to make the charges add up to 0. There we go. Right, so those are essentially displacement reactions, and we've done a lot of practice of writing out chemical equations and also using the charges of our ions to write the correct chemical equation for each compound. The next part we'll look at redox reactions in more detail and go more into half equations and ionic equations.